Okay, stream is live. Couple quick pieces of business. One, there were a couple of bugs in the two of the Canvas assignments. So one of them was I was missing some decimal places on one of the questions in the master theorem one. So I fixed that and put a little note to round to 2 decimal places on it because it's 1 point something or other, and I had forgotten the something or other. So yeah, should be good. And it's pretty obvious that what it rounds to because the third digit is a 1. So it's like 1 point something something 1. So it rounds down. Yeah. Okay. So my bad. And then I had made some just slip ups on the Turing Machines A assignment where I had the wrong answers coded as the right answers, but it's fixed now, so everything should work fine. Yeah, if you guys ever find what you think is a mistake, it's likely due to my incompetence. So, you pay how much in tuition, and all you guys get is Ed Jerome and jerks like me, right? You really should get a refund. So, all right. So let's get to it. What we're going to start talking today is kind of to peel back the layers in terms of how a processor sort of actually functions. And so to kind of motivate this, let me start with a very simple program that I've written, in this case in C, but it might as well be in Python. Who cares? Okay, so all I'm done here, nothing particularly exciting, is define 2 variables, A and B. I've set their values to be 1 and 2 respectively, and then I'm defining C to be the sum of the two. Yay, how thrilling. So if I want to run this, you look at high-level code like this, and we kind of treat it as if every single line is one exact instruction. So, for example, adding 2 numbers is a single instruction, and that's not necessarily true. So, for example, let me actually doctor this up and add. Let me make this more complicated just for fun. Something like that. Okay, so I'll define, and it's an int, not an end. I'll define 3 integers, a, b, and c, and I'll define d to be a times b plus c. Okay, that formula looks like a single operation, but really how many operations is it? 2, yeah, because the multiplication is 1 operation, and then I'm taking whatever that result is and adding c to it. Okay, so this line of code looks like it's a single operation, but it really is more than that. And it can be a lot more than that depending on what the actual instruction is there. Okay, so what I want to kind of do is start to peel back the layers, and we're going to go basically from the highest level of programming, which is in some sense what we see here, okay, or something in Python, and kind of zoom down to the level of the actual processor and what the processors actually do. Okay. Okay. So this is a unit I'm going to call, for lack of a better way of putting it, the hierarchy of programming. Okay. So I've got that. Fine. And let me do the following. I'm going to have this program process that for me and turn it into sort of one layer lower in terms of the hierarchy of programming. And I'll explain what the layers are in a minute. Okay. Which is this, which is called assembly. And let me choose the correct syntax highlighter. Okay, so I look at this, and does this look human readable? Kind of, right? Is it less human readable than what we had a minute ago? 100%. But it's more human readable than what I'll show you in a moment, okay? And in particular, we may not know what all of these symbols and words and stuff mean, but we could maybe spot two things that look familiar. In particular, lines 20 and 22. What do I think's going on with lines 20 and 22? Yeah, well, what was it that our program did there in terms of some arithmetic? It did a multiplication followed almost immediately by an addition. Yeah? Okay, so somehow that line of code that I wrote that just defined D to be A times B plus C, and I just made that up, right? There's something special about A times B plus C, um, really translated into a pair of actual machine operations, okay? So what we're looking at here is what's called assembly, and in some sense, it's the second lowest layer that you can look at in terms of code. Okay. All right, let me show you the lowest layer that we could look at in terms of code. So one moment, please. Okay, so I've done the exact same thing here. And let's look at, say, for example, this multiplication line. Okay. All right, so what we have there is a bunch of numbers. The first one is a line number, so line 20 of my code, fine. 0024 is just basically counting how many instructions I am down into my program. Okay, we can ignore that for the moment. The part I want to really concentrate on is this big chunk of 8 hex characters, so that corresponds to 32 bits worth of encoded data. Now I look at that and I see 207C001B. Is that human readable? Like you can read and see what that value is, but does that mean anything to you? No. And for that matter, do any of the other ones mean anything to us? No. Like I have no idea what any of that stuff means. Okay. So these 16 or excuse me, these 32-bit instructions are actually the ones and zeros that the processor is going to deal with. Okay. But for a complicated instruction set like the one we're looking at is 64-bit ARM. So that basically, this is the language that my Raspberry Pi speaks and every smartphone in this room. Okay, because you're all, you all have, well, even the Androids that most of you, who has an Android phone, by the way? Okay, get out. Um, it's okay. But what's the processor in it, or do you know? It's probably a Qualcomm, like a Snapdragon or something. Okay. Well, Google it real quick, right? For what's the processor in your particular phone? Okay, all of the iPhones in the room are running ARM architecture processors. So actually, in some sense, they're uh, like first cousins to what's in my Raspberry Pi. Okay, is maybe the best way to put it. Okay, so the machine language or the actual ones and zeros that the processor is going to deal with are displayed here in hexadecimal. Okay, and obviously we could expand that out into the big binary number, but it's just a bunch of ones and zeros, right? I look at that and I'm like, got me, right? Now, if you stare at it for a few minutes, you might kind of start to suss out some patterns, right? But there's a lot there. And in particular, it's 32-bit stuff. So how many 32-bit numbers are there? A lot. It's 4 point whatever billion, right? So good luck like sniffing out the entire pattern, okay? And in fact, to learn the entire pattern would require basically delving through a programmer's reference manual from ARM that's several thousand pages, okay? So we're going to not look at this particular processor architecture. We're going to look at a much more simplified one that was made up by the guy who wrote our textbook precisely for the purpose of teaching. Okay, so it's simplified enough that you can understand it without having to read several thousand pages of documentation, but still robust enough that we can do most of the kind of interesting things we might want to. Okay, like adding numbers or something like that. Okay, Now, interestingly enough, it isn't capable of doing hardware multiplication. But is that a problem? It's maybe inconvenient, but do we have to have the ability to do multiplication with a computer, like as a hardware instruction? Could we do it some other way? How can you do multiplication without doing multiplication? Yeah, you could do repeated addition. Okay, we saw that actually when we did bare bones, right? That you could implement multiplication by means of repeated addition. Okay, is that the only way to do it? As it turns out, no. And maybe later we'll talk about some of the other algorithms for it. It's kind of interesting. Okay, so the hierarchy of programming is, and let me kind of sketch this out on the iPad just to kind of give it a pictorial view. Is something like, why do we not have any display on the screen? Okay, why am I not getting any display? Let's switch back. Okay, why am I not getting any display out from my iPad? One moment, please, technical difficulties. Okay, I have no idea why this isn't working, guys. Okay, well, we'll go with plan B then, which is I'll type it instead. I'm not sure why this isn't working. Sorry. Okay, so let me just open up a, let's see. Let's just do a text editor. We'll be real fancy. Okay, so let me blow up the font size too so you guys can see it. Okay, so at the top layer, we could have something like high-level coding, which would be like C, Python, Java. What other languages have you guys maybe used? Rust? Uh, huh? Yeah, C, C++, C Sharp, Objective-C, Swift. Okay, and we could go on and on, right? There's tons of high-level languages. Okay, now at the bottom end, so let me do this. We have machine code. And for a very simple architecture, okay, or sort of a historical one like one from the 80s, it's not that bad to uh, to be able to read machine code by hand. And what we'll see with our toy architecture is that it's simple enough that we can do that. Okay, but for a modern architecture like 64-bit ARM, uh, good luck, you know, decoding it all just by memory. There's just way too much. Okay. So back in the day, when computers were first uh, things that were around, okay, so like let's take, for example, the ENIAC. All right, where was the ENIAC and what was it built out of? And when was it? You guys remember? Huh? Yeah, it was in the 40s during the war and the immediate aftermath, right? Okay, where was it? Yeah. Uh, I thought it was in DC. Well, it certainly is now, but yeah, so East Coast someplace. Okay. Uh, what was it built out of? There's a bunch of vacuum tubes, right? And here's the part that was really the kicker back then. How did you program it? Well, you didn't in some sense. So, have you guys all seen pictures or video of the old school like telephone relay system? So you'd call up, you'd lift the phone, and somebody at the other end would say operator, and then you would tell them like a number or whatever, and they would say 1 moment, please, and then they'd be pulling out wires from plug boards and plugging them into other places, yeah, to connect you to whatever call you were trying to get to. Okay, well, in some sense, that's how ENIAC was programmed. So you had to physically remove wires and plug them into other places to change the program. Now, as you can imagine, was this practical? No, horribly not. Okay, um, and so later, uh, machines were capable of where you could load in a program on like punch cards or something, or magnetic tape, or paper tape or something. But you would have to program them in the machine code, and so you would have to know the patterns of the ones and zeros and write all of that stuff yourself. Now, as you can imagine, this is not particularly practical except for eggheads like me, right? And it's not really practical for eggheads either because you could do it much faster, okay, if you have tools at your disposal. So one level up from this is what's called assembly. By the way, the person who invented the first assembly language, Kathleen Booth, died, I think, last week at the age of 100 and something. So, like, yeah, this is, recent history in some sense. And what assembly language is, each line of assembly language corresponds exactly to one machine instruction, but assembly language is at least a bit more human readable. Okay, so what we are looking at here on the right hand column, so for example, this instruction here, move W0, comma 3. What do you think that's doing? Right? You don't have to know the actual instructions to get a sense for what do you think is happening there. Yeah, the number 3 is going someplace. Okay. All right, where it's going and all of that detail we'll talk about later. But then we also have like mall. What do you think mall is going to do? Multiply some stuff and stick the answer someplace. Okay, so you don't have to be a rocket scientist to be able to read this once you know sort of the basics of the language. Okay, and this is more practical than just bare machine language, but still nitty gritty enough that every assembly instruction corresponds exactly with one machine instruction. Okay, so it's sort of a slight abstraction of this. Okay, so if we go back to our little text document here, okay, what you guys do when you program in a high level language is you produce something that looks like what we started with, okay? And then two programs process that file and eventually spit out the machine code, okay? The one that goes from high level to assembly is called a compiler, and the one that goes from assembly to machine code is called an assembler. And those sort of things, to some extent happen automatically in the background, and you're not necessarily realizing that they're happening. Okay. So you're translating from this high level stuff down to this very low level stuff. Okay, good? Yeah. Okay. So now let's look at um, an actual assembly language for an actual processor. Okay, so let me go over to the Mac and okay, so I'll share a link to this on Canvas. Think of it at the moment as very much a work in progress. I've been working on this for years. So the author of the book defined this set of instructions, okay, and I've made some minor modifications to one of them. Um, it has 12 instructions. And here is all the binary for it. Okay, so let's look at what basically we have at our disposal. We can move data from one place to another. That covers 4 of the instructions. Okay, seems reasonable to be able to move data to and fro. Okay, should we be able to do addition? Probably going to be kind of important. Should we be able to do some of the logical operations like AND, OR, and XOR? Yeah, probably useful. We'll talk about this bit rotation thing later. And then something that we saw with bare bones and with the Turing machine is we have to be able to make decisions. If then, or if something, then do something else. Otherwise, do a third thing. Okay, that's what makes a computer is having a conditional, the ability to do conditional expressions. Okay, well, there's the entire instruction set, all 12 instructions. That's not particularly bad to sort of, like, could we have all 12 of them in our head without too much trouble after a little bit of studying? Yeah, not unreasonable. Okay, now to contrast this with a modern platform, like, say, for example, the Raspberry Pi or your iPhones or whatever, did you find an answer to your question or a Google Tensor? Okay. I don't know what architecture that is, but I'll look it up later because I'm curious. Okay, so 12 instructions, not horrible. Now, on the other hand, you might say, well, but there's a few that are missing. So, for example, is there a multiplication instruction? Nope. And so if I was trying to write a program for this processor that did multiplication, how would I have to do it? Either repeated addition or some other wizardry. Okay, so this is sort of the barest set of instructions that we could possibly have and still do interesting things, but not be so complicated as a modern processor that has thousands of instructions. Correspondingly, it has several thousand pages of manuals. Okay, so you want to learn a modern architecture, you take something like CS241. That's the entire point of the class. This is, again, just supposed to be the little amuse-bouche of it. Okay. All right. So let me, it would be really nice if the iPad would work. And I do not know why it is not. This is really quite annoying. It worked fine this morning. So, okay, well, we'll just have to go to plan B. Okay, so let me sort of shift gears for a moment and let's talk about how a processor actually sort of looks and what is inside a sort of example processor. Okay, so this is a kid's book from the 80s called Machine Code for Beginners. It was written by or published by a company called Usborne, which still publishes kids' books. A lot of them are scientifically oriented, you know. So if you want a book that's got all about dinosaurs for your 6-year-old, they have such books. Okay, but in the 80s, they had a couple of these tech books, and they were the first people that actually did like very colorful, very sort of kid-friendly, if you will, books on computer programming. I never actually had one of these books as a kid. I kind of wish I did in retrospect, because looking at it, if I had had this when I was 7 or 8, I would have gone absolutely ape with it. Yeah, who knows? Maybe I would have ended up inventing Facebook or Twitter and becoming rich. But alas, you guys have to just put up with me instead. Okay, so what's inside a processor? Processor has the ability to do arithmetic, so it has a sub-circuit unit that can do things like addition and subtraction and whatever, okay? It also has these special little mailboxes that are called registers. And when you hear register, what do you think of? Like, what's a register? Well, you go to the store and you pay for something. Where do you take it? The people at the cash register. Even though How many of you guys have paid for something in cash in the last month? Yeah, we're not really using cash all that much anymore, but you take it to the cash register. Okay, it's an old-fashioned term because what would have a cash register looked like, say, 100 years ago? Well, it would be a lot bigger. It wouldn't have been a computer, right? It would have displayed, for example, the amount of money in the drawer. And as you pay for things, you know, so and so would add up the things to the total, or maybe subtract if it was a bank and they were giving you cash, like say you're cashing a check or something. All right. So it's this mechanical thing that showed you at any moment the total of something, right? It's sort of like a running counter. Um, Maybe a good example of this would be the odometer in your car, right? Is kind of a register. It just only ever counts up because that's its purpose. But you could imagine one of those that counted backwards also, like if you went into reverse or something. Um, Spoiler alert, that doesn't work. You can't knock 100,000 miles off your car by driving it in reverse and then selling it, right? No. Okay. So these registers are, in some sense, special little pieces of memory. They're only able to hold what the processor is currently dealing with, like in terms of its arithmetic and whatnot. And what we're looking at is a diagram for what a processor from the 1970s and 80s looked like. I probably mentioned this guy before. It's the old MOS 6502 that powered what machines, for example, the 8-bit Nintendo, the Apple II, the Commodore 64, uh, the BBC Micro, a whole bunch of other machines of that era. Okay, the 8-bit Nintendo, that probably got your attention, right? So this is the processor architecture for it. It had basically 4 or 5 registers. This one called the accumulator. That's where the arithmetic happens. X and Y are called index registers. There's this thing called a stack pointer. There's this thing for flags. And there's this thing called the program counter. We'll talk about what those things are in a moment. Okay, so pretty simple architecture. So the particular processor we're going to look at has a simulator to it. If I can get the website open. Okay, so let me go to here. Okay, so here's the simulator that kind of displays what our processor looks like. Okay, so our processor has 16 registers, and they're labeled 0 through F. It also has 2 special things called the program counter and the instruction register. We'll talk about those in a moment. And it has a glorious 256 bytes of memory. Okay, how much memory are in modern computers? How many bytes roughly? So RAM, how much RAM is in a modern computer if you were to go out and buy one today? Yeah, probably 8 to 16 gigabytes at minimum, right? You're building a beastie gaming rig, probably more like 32, maybe 64, right? You want a server, more than that. Okay, so gigabytes. In the 80s, the computers of the day had like kilobytes worth. And our machine has 256 bytes. That's it. Okay, so a quarter of a kilobyte. Not very big. But it's small enough that we can get our hands dirty and understand the entire function of this machine, but still rich enough that we can actually do interesting programming for it. Okay, seem reasonable? Okay, so I've loaded in here a sample program. And a program is just a bunch of ones and zeros and stuff in memory. Here it is. All right, now if you look at that, is it at all obvious what that program is going to do? No, of course not, right? Because we don't know what the machine language is that goes with it. We'll see why it is what it is in a minute. Okay, but how is the processor going to actually execute this thing? right? That's essentially the level that we're at now. Um, okay, so this is where this thing called the program counter comes in. Okay, the program counter is what we call a pointer. It points to where data is located. Okay, so for those of you who are independents, right? So Curtis, if you get a birthday card in the mail, how do you receive your birthday card? You go down to the mail room. Okay, now the mail room, well, if you've got a package or something, right, which is probably what most of you guys are getting through the mail nowadays, you go to the mail room, they give you the thing, and off you go. Okay, but what about if it's just like a letter or a card? Yeah, you go to your little mailbox, and how do you know which mailbox is yours? Okay, you get, of course, an email at the beginning of the semester, because what doesn't function around here without an email, right? And if only we could take more things to the classifieds so we wouldn't get so dang many emails, right? Okay, so you go down to your mailbox, right? And you know what number it is and you know what the combination to open it is because you got that email at the beginning of the year, right? So let's assume just for the moment that none of the mailboxes are locked. Just work with me. Or you're the mailroom employee, so you're on the backside where you can just put them in, right? So you got all these mailboxes. If I tell you a mailbox number, is that the same as what's in that mailbox? So let's say I tell you mailbox number 147. I'm just making that number up. What's going to be in mailbox 147? Who knows, right? So for our purposes, let's imagine that all of the mailboxes hold exactly 1 byte of data. Okay, so 8 bits worth of stuff. And so inside each mailbox is like a little index card and it's got a number written on it. Okay, so let's say I go down to mailbox number 2F and I open it up. What am I going to find there? Some number, right? Is it going to necessarily be equal to 2F? No, okay. So what I'm trying to contrast here is the difference between the mailbox number and what's at that mailbox, what's inside of it, okay? The mailbox number is a pointer, right? So it tells us which mailbox to go open. The program counter, or PC for short, is a mailbox number, okay? So when this machine fires up, the program counter will always start at 0. Makes sense, got to start someplace. And what it's doing is pointing to memory, where's the next mailbox I need to open to start loading in data to process? Okay, so if it's 0 initially, where is mailbox 00? Well, it's at the top left corner. Okay, I need to load that in and do something with it. And when I load something in, what should I do to my program counter? Add 1 to it, increment it, so that it now points to the next memory address. Okay, make sense? Okay, now, on this particular architecture, every instruction requires 2 bytes of data to encode. Okay, so I need to load in a byte and then load in the next byte in order to have a complete instruction. Good? And those bytes will go into this special register called the instruction register. Okay, so let me fetch those 2 instructions and let's see what we get. Okay, so what is in the instruction register now? 2-1 went to the first byte, 0-1 went to the second byte, and what's my program counter? 0-2, which would point to the next instruction, which we'll get to later. Okay, does that make sense? It just pulls in 2 bytes. There they are. It's an instruction. Now, the instruction is 2101. Do I have any idea what that means? No, no clue, right? It could mean anything for all I know. Well, so the next step is I have to decode what that instruction means. Yes? Okay, now how do I decode it? Well, let's go back here to my table. All right, so operation number 2. What is this going to do? Load register something with a specific number something. Okay? That's what operation number 2 does. So if I go back to here, you see that this 2, the very front character or hex nibble, is a 2. That in this language is called an opcode, and I can look at the 2 and know, that's the operation that takes a specific number and puts it into a specific register. Okay, and there are only 16 possible opcodes, so it is not outside the realm of possibility to just memorize all of them. Okay, or we just look at the table. So what's opcode 2 do? Loads a register with some sort of number. Okay, what number and which register is it going to go to? Well, I wrote it here as 2RXY. So what are RX and Y in my example? R is 1 and XY is 01. Okay, here. So what register do you think this is going to load the number 01 into? Register 1, and what's the number that gets loaded in? 01. Okay, so you see how we've looked at that and decoded it? The processor has to have circuitry to do that same thing. Okay? So let me step one cycle, and the decoding just happened. So what does that instruction mean? It means take the number 01 and put it where? Register 1. Seem reasonable? Okay. Well, let's look at the next instruction. Oh, sorry, before I do that. So there's 3 steps here, right? Fetch the instruction in, decode it and figure out what the hell you're supposed to do, and then actually do it. And there we just did it, because now look at register 1. It has the number 01 in it. Yes? Okay. So next instruction, 2202. How could I decode that? Well, it's the same operation, right? So what does opcode 2 do? Takes a number and puts it where? In a register. Which number? 02. Which register? 2. Okay, so decode, execute, and look what we got in register 2. Make sense? Yeah? All right, so let's keep going. Next instruction. Ooh, this one's different. Which operation are we doing now? Operation 5. What is operation 5? Do we remember? Nope. So we go back to the table. So what's operation 5? Yeah, it adds registers S and T and it puts the result in register R. Okay, so this is our addition command. All right, so let's go back to the thing. 5312. So I'm going to add, that's what the 5 stands for. Which registers get added together? 1 and 2, and where does the answer go? Register 3. Okay, so does that make sense? I mean, assuming that everything on that table that I showed you was correct. Okay. Okay, now this begs the question, where did that table come from? The author made it up. Okay, so whoever designs the processor has to make up such a table. Okay, because otherwise you're not psychic, right? Okay, what else could this instruction have been? Could it have been 5321? Is adding register 1 and 2 the same as adding register 2 and 1? Yes, same result, right? Can you add in any order you choose? Can you subtract in any order you choose? No. Right, so you got to be careful, but addition, no problem. Okay, so what should we expect to end up in register 3 after this instruction executes? 03, because what was in register 1? What was in register 2? And if I add those, I get, last time I checked, 1 plus 2 is 3, yes? Okay, so let's step through one more time. Add, and bam, there it is. Okay, next instruction, 33FF. Do I know what operation number 3 is? Have we hit it before? We have not. Okay, so back to the table. What does operation number 3 do? stores it to a mailbox. Okay. So now that I've done some arithmetic, I could say, all right, I want you to take the number that's in this register and go put it in that mailbox. So what do I have to tell you for that to work? I have to tell you which register and which mailbox. Okay. All right. So if we look at this here, 3 is going from a register to a mailbox. Which register? 3. Which mailbox? FF. And look what's down there in mailbox FF. Okay, the number 03. Okay, so I can load data in from memory. I can load specific numbers in from memory. I can process data, and I can stick it back out into memory. Okay, and by process data, I can do addition, several logical operations, and a rotation operation, which we'll talk about why that's useful later. Okay, that's it. Doesn't seem like a whole lot of pile of instructions, does it? So could we program a multiplication routine with this language? Yeah, with a little bit of work, okay, because we need to talk about how do you implement loops, how do you do if-then statements, how do you do all of that kind of stuff, right? But we have the fundamental pieces that if you think about it, are not actually all that different from bare bones, right? Because in bare bones, how could I set a value of something? I could init it. How can I add or subtract? Well, we had the increment and decrement. There is a while loop construction, which, as we saw, could be used for a lot of things, right? And that was it. Oh, we could also clear, right? Set something to be 0. Okay, so this isn't a very huge instruction set, but it's enough that we can do interesting things and still understand every single piece of it. Okay, now, would you guys agree that just spitting out this machine code is not practical to just have it all memorized? Okay, you might be able to memorize it in the sense that, like, if you were teaching this every semester in a row for a few years, you just know these instructions by memory. Okay, and I do. You guys don't yet, and that's fine. We just started looking at this. Okay, so the book, the author of the book basically defined this machine code language. Okay, and remember, what was our hierarchy? High-level programming, assembly, machine language. So he defined the machine language, but never actually defined an assembly language for it. So what have I been working on for the past few years? The assembly language. Okay, so let's take the program that we just looked at and let's look at it in 3 different views. Okay, which is, would you guys like that view better, the one with the 5 bullet points that's on the screen? Okay, is that a valid program? It's written in English, but is it very obvious what it's doing? Yeah, because you can all read. Okay, this down below, those 5 lines, is the assembly version of it. Is that closer to the machine code, but still pretty much human readable? Yeah, okay. Now, what's with these semicolons and the stuff after that? What are those things? What are those called? They're called comments. Okay, so the stuff that's after the semicolon is ignored by something that's going to process these instructions. They're written there for the human typing it, not for the machine. Okay, it's always good to put comments into your code. It makes it more readable for the poor schmuck that. So, like, let's say you guys write some big pile of code and you send it to me and it has 0 comments whatsoever. I'm going to look at it. Am I going to be able to figure out what's going on? Well, maybe. Okay. But if it's like, if you've gone out of your way to make it as nasty as possible, maybe I wouldn't. What'd you say? Yeah, that's true. It's not rocket science. Okay. So I might be able to read it, but if you sent me several thousand lines of code with no comments whatsoever, like I'm not going to be able to read it. Okay. Or I could, but it might take me hours to figure out what was going on. Whereas if you put in some comments, it might help me in that process and only take an hour instead of multiple hours. Okay. Okay, so what the author didn't do was basically this layer of the translation. Okay, so I've made that up and I've been refining and adjusting it and stuff over time. Um, and I actually just realized looking at this document, I need to do some very heavy editing of it in the next 24 hours. But it still looks human readable. Okay. So this is the corresponding machine instructions. So how did I get 2101, 2202, 5, and so on? Right. Well, I had that table in front of me and I thought about this and I realized how each instruction corresponds exactly to one set of binary numbers, okay? Because I knew the table, yes? So how did I produce this list of numbers when I did it on my Raspberry Pi? Did I produce those numbers? No, I had a program do it for me, right? So I gave it this code, my assembly code, and it spit out the machine code for me, right? That program was called an assembler. And I've got good and bad news for you guys. Is there an assembler for this language? In May, there was no assembler for that language. In July, there's a mostly working assembler for this language. And how do you think that assembler came to be? Well, actually, in this case, John Barker built it. How many of you guys know John Barker? Works in the QSC, computer science major, senior. So he and I spent the summer doing research, and Owen Runge also. And what they were working on is building the assembler for this language so that you could type in this and it would spit out that. Basically, all you would have to do is click a button. That'd be pretty handy, right? So, what was I working on this summer? This processor that's described in this document doesn't actually exist. So, I set about to actually build it. And I've got maybe 80% of the way. Um, so, I built it at least in a simulation kind of environment. Haven't actually fabricated it yet, but that's I'm getting there, right? To build this ridiculously old processor from that would have been terrible in the 1940s, but hey, why not, right? Okay, so that translation routine, at least as of right now, you basically have to do by hand. But is it that hard to do it by hand with that table? No, it's a little annoying, but you guys can do it. Okay, so does that kind of make sense? Okay, so so that's where we're kind of going with this is to start to sort of look architecturally at the machine or a machine, and then you can imagine a modern computer as just being take what we're doing and add 50 years worth of development onto it. Okay. Um, the other thing I want to do at least a little bit of is to look sort of from a circuit level. Like when we built with the transistors on the breadboards, right? We built several logic gates. We built AND gates, OR gates, XOR gate, right? And so on. How would I combine some of those to do binary addition, right? So if I give you two binary numbers and I ask you to add them on paper, you know how to do it. How do you build a circuit to do the same thing? Well, requires a little bit of thought, right? Okay, so we'll look at some of those sort of simple things. And then you can imagine a processor as just being hundreds upon hundreds of those gates put together in clever ways. All right, the smell of pizza beckons. So I don't know if you guys all saw the email about we've got some guests from another university doing engineering slash computer science. They brought a whole bunch of toys and other cool stuff. There's going to be a really awesome lunch talk just down the hall. Yeah? All right. See you guys later.